paper out? Everybody?
Are we taking the quiz tonight?
Well, no. This is what we're doing is we're just kind of reviewing the old quiz, making sure we're good with it. So here's the 4 problems. Here's one of them. Here's another one of them. Here's another one. And last one. Okay, try those 4 problems. Give you guys about dates. Let's see if we work through these. Very first question is 2x times x to the third, which is the same thing as saying 2x, or 2 times x to the third, or 2 times x times x times x times x. Anyone want to take a shot at what this answer should be? And how are you deriving? Go ahead, Preston.
2x to the 4.
2x to the 4, I completely agree. Now, can you explain that to us a little bit?
Yes. Okay, so whenever you have a power, that means it's just that number times itself. So if you have another one of that number, then you just add that onto the power.
Perfect. I like that. So, what Preston is saying is basically this. So how many x's are all strung out in a row, multiplied together? That happens to be 4 of them. So this answer comes out to 2x to the 4th. Would anyone like to take a shot at this one? Y to the 6th power times y to the negative 6th power. Go ahead, Reese.
I'm going to take a wild guess.
Go for it.
And say that it's y negative 1.
Okay. How would you get to negative 1 on that by chance?
I don't know. That's why I'm saying it's a
Wild guess? So if we're following suit on this problem, we're adding the exponents, Reese.
Okay.
What is 6 added to negative 6?
Negative 12.
Whoa, going the wrong way. 6 added to negative 6.
Oh, is it 0?
It is 0.
So it's just y.
So it's y to the what power?
Nothing.
To the nothing, and y to the nothing, which is y to the 0, is equal to
1.
1.
Guess what that looks like? Looks like yo 1.
Yo, 1. I'll take it.
Yo Hans Sebastian.
All right. Anybody want to take a shot at this next one? Go ahead, Summers.
You distribute 2 to 3 x to the third.
Perfect. Comes here. Comes here. So that becomes 3 squared x to the 6th. Hey, why is that x to the 6th, not x to the 5th?
Because it's different for exponents.
So power raised to a power. When exponents are on top of each other, they multiply. Okay? 3 squared is what? 9. And x to the 6th, is it okay to leave it as x to the 6th? All right, so there's the first 3 answers. All right, 4th one. Go ahead, Angelo.
No, I have a question.
Talk to me. Which one?
Why wouldn't you just add the exponents when it comes to?
Are we talking about this 3rd problem that we just did?
Yeah.
Okay. So let's think about this. If I have 3x to the 3rd, and that quantity, does that make sense if I say the word quantity, meaning it's in parentheses, is squared? So if I take this off to the side a little bit, this is the same thing as saying this. That make sense? And the reason I wrote it twice is because this was to the 2nd power. Okay, so now it's going to be 3 times 3, which is 9. X to the 3rd times x to the 3rd, which now, what do I do with the exponents now when they're being multiplied? I add them. That makes sense?
Because what I was doing was I was distributing it over 2 places.
Oh, I got you. Do you see where your error took place? Feel good about it? 4th problem up there. Go ahead, Bo.
So you distribute from 2x to the 2x on the outside?
Okay, so here, here, and here. Is that what you meant?
Yeah.
Okay, so what do I get here?
You get 4x.
I get 4, and then what else? What does that become?
X.
X squared. And this becomes? So y to the 4th to the 2nd.
Oh, yeah. 8.
Y to the 8. And again, let's look at this. Angela, this is going to be the same kind of question. How many times am I going to write this? How many times will we write that? How much?
8 times.
So I have this times this. because of that. I wrote it twice. And then 2 times 2 is 4. X times x is x squared. X to the 4th times x to the 4th is x to the 8th. So 2 different ways to look at it. So you could distribute it, or you could remember to rewrite it all the way down. So any, yeah, go ahead.
Okay, so X, why is it 2? I don't see it.
Okay, so remember in math, if you have just a letter sitting by itself, it's actually to the first. So x to the first, x to the first. If it's x to the first times x to the first, we have to add the exponents. You're counting them. So remember when you have like bases with exponent, and they're like bases with the same exponent, and you're multiplying them, you're counting them, they're next to each other. So let's take this and do a whole string of it. Is that okay? Yeah. The reason I wrote it twice is because of that. So now, like bases, so 2 times 2, you're okay with the 4, right? How many x's do I have? 2. So x squared. How many y's do I have?
4.
And
8. Oh, yeah.
cool? Like it? So a like term would be like bunnies. If bunnies are all standing out on a field, you're like, oh, how many bunnies do I have? You count all the bunnies. So I have X bunnies to the whatever power. So you add them, you count them. We good there? All right, let's throw another 4 questions up. Everyone feel comfortable with these 4?
Yeah.
Okay. Here we go. Same rules apply. Okay, 4 minutes to try those 4 questions. All right, so we're trying to get rid of that negative exponents, meaning it's going to become a reciprocal, meaning it's going to move. It's going to switch from a top position to a bottom position, or a bottom to a top, depending upon where we're dealing with it. But a lot of times you can do the math without worrying about the negative exponent and take care of the negative exponent towards the end. Or sometimes you can take care of the negative exponent at the beginning and then do it at the end. X raised to the negative 2 power. It's a negative exponent. It doesn't like sitting there like this. So where are we going to go? Go ahead.
Put it below 1.
It put it below. So if I put this below, can I just leave the top blank, or what should I put there for the blank?
1.
A 1. Where did the 1 come from?
It's already there.
It's always been there. In fact, there was a 1 that was in front of this originally, but again, we as math folks decided, well, we're going to be lazy because it takes so much work and energy to put a 1 in front of something. Okay? And that's where it gets goofy, but this problem is exactly appropriate. Okay, so the negative exponent, it switches. If it's not looking as a fraction, you make it a fraction, and then you move down the part that has the negative exponent. What about this second one on the bottom? Do what? What's 1? The whole thing is 1?
Yes.
No.
No.
Oh, wait.
But it's like totally written out. There's like tons of stuff. We got a 3, we have an X, Y, and Z.
0 to
No, you know it's 1.
But how is it 1?
Stop.
everything raised to 0.
Yeah, we have this whole thing. This whole thing is raised to the 0 power. So no matter what they put in here, that makes it all goofy. It comes out to an answer of just 1. Done. Huh. That's kind of goofy. All right, what about that third problem? Is there anything that has a negative exponent?
Yes.
What has the negative exponent?
Why?
Y. So what wants to move?
Y.
Y. Where does Y want to move to?
Down.
It wants to move downstairs. This 3x company is out of control. So This is the only one that wants to move. So the 3x to the 5th are totally content where it's at. The reciprocal of that comes down here. Done. Sweet. Now, the fourth one is a problem that we could work on without worrying about the negative exponent, or we could take care of the negative exponent first and work on the rest of it. But we have to realize the whole thing's grouped. What do you got?
I got 25A6.
You're pretty close. You're really close. I like it. So I think what you would have done is you would have distributed here and here, and it should have came out to this. Why is it negative 6 right there?
Wait, it's times itself. Oh, wait, no.
You're not.
Yeah. So then this should come to this as an answer. Okay? Now, let's work this another way. Let's bring it over off to the side. So this is the same thing as saying 5a to the negative 3 times 5a to the negative 3, in which I could go 5 times 5. Oh, that should be a 25, right? Oh, boy. Can't take that anywhere. So that gives me the 25 right here. And then I have a to the third, a to the negative third plus a to the negative third. So if I add those together, I get a to the negative 6, which is that gives me this answer, which then this answer yields to. Or some of you might be looking at this problem going, well, why could I have not had this done? Why did that become a positive 3 now? Why could I go from this step to this step? Well, it started out with a negative exponent, so I moved that first. Now I can distribute that here and here. Done. Yeah.
So I thought that it was like there's two sets of it.
Mm-hmm.
So you're not multiplying it. I got the different answer.
So if you go exponent raised to an exponent, you're going to multiply. But if you realize exponent raised to an exponent, if like let's say this exponent, the top exponent, the outside exponent is like 7, you would write your grouping 7 times and then multiply it all together.
So wouldn't the answer be like?
But think of what the basic definition of multiplication is. Okay, 3 times 4 is the same thing as 3 plus 3 plus 3 plus 3, or 4 plus 4 plus 4. So multiplication and addition go hand in hand. Multiplication was a way that you could group things together quickly to count them up. Is really how multiplication came about. Rather than go on trying to count 1, 2, 3, 4, 5, you can say, oh look, I have all of these rows. I have 10 rows of trees, and there's 16 trees in each row. Rather than going 1, 2, counting all the trees up, you could go 16 times 10 and get the 160 trees. So it's a way to group things quickly together in order to formulate how many you have. That's what multiplication is. Now, this question came out yesterday, and I said I'd get back to you on it. Somebody asked why the negative exponent. Why did the negative exponent work as a reciprocal? And this is what was presented to me, and I thought this sounded pretty good. Okay, so let's start with 2 to the third. 2 to the third is the same thing as 2 times 2 times 2, right? Which is the same thing as 8. 2 to the second is 2 times 2, which is the same thing as 4. 2 to the first is just 2, which is just 2. 2 to the 0 is 1. And then I get to this. This means reciprocal. So this becomes 1 over 2 to the first, which is 1 over 2. This is 1 over 2 to the second, which is the same thing as 1 over 4. This is 1 over 2 to the third, which is 1 over 8. And that's why the negative exponent works the way it does, just using a base of 2, but it's going to work whatever base you deal with. Okay? Last 2 problems I want to work on for this, and then I have a little bit of a lesson, which I think you guys will be okay with. Okay? Only 2 questions left. Clear ink. try those two. Give you 3 minutes to do those two. A little longer. Double check with your neighbor. We got some negative exponents, we have some positive exponents, we have just a fraction of exponents and stuff. More seconds. What do you think? What should we do with the first one? Brennan?
Move the a to the -2 on the top,
Okay, so this is going to move up, okay?
and then the b -3 on top.
Okay. Anything else going to move?
It becomes a to the 5th and b to the 8th,
Okay, so you get a to the 5th, b to the 8th,
and then
c to the 7th, over c to the 4th. Let's pause there. I like where you're going. I like it. So how did that become a to the 5th? Anybody else? Go ahead. Yeah, I went a to the 2nd, I moved it up top. Then it becomes a to the 3rd times a to the 2nd. And when you're multiplying like bases together, the exponents we count. So it becomes a to the 5th. And then b to the 8th took place, same thing. B to the -3 moves up, becomes b to the 3rd. So on top I have b to the 5th and b to the 3rd. So again, like bases, when multiplying, we add the exponents. We count them up. So it gives me to the 8th. What's the last step, Brenna? Tug of war between the top and the bottom. I like it. Top's going to win by 3. So a to the 5th, b to the 8th, c to the 3rd. Done. Okay. So the difference between the first one up there and the second one we actually have to reduce a fraction. So this is like saying that we have 5 over 10, and then you have the rest of the problem. Correct? So let's take care of the 5 over 10. What does that reduce to? 1 over 2. Okay? All right, so that's what we're going to reduce to. So there's more to the problem to this. I probably might not need to have the 1 up on the top, as long as I have some other letters and stuff up there. But if everything moves to the bottom or cancels out with tug of war, we can leave the 1 up there. All right, so x's. What happens with the x's? They cancel out. Why is that? Tug of war, tie game. No one wins. They're gone. What do we know about the y's? 1 has to come up top, 1 has to go on bottom. Why did that happen? They were both negative. They both didn't like where they're at. They flip-flopped. What's going to happen with the z's right now? Tug of war. Who wins? Bottom by how many? 2. Is the problem done at this point? It's not quite done yet. I think we could still do a tug of war with the y's. Who's going to win? Top. If the top wins, do I still need to have the 1 up there? You don't necessarily need to have it up there, but top wins. Done. Wait, what? I technically don't need to have the 1 there. Is it y squared? Oh, why is there a y squared there? Who put that there? Don't start blaming me for that stuff. Go. Is that more like it? Okay, I can do math these days. Woo! Okay, what do you think? We still have a little bit more to work on with the quiz, and we'll focus on a little bit on that next week, which I think we really do need to take care of the scientific notation. I think that's a pretty good way to kind of help you out a little bit, make sure you feel comfortable, and it is recorded, so you can always review back to it. Can I clear this? All right. Kind of a quick lesson. So, prior to the big calculators, this method is called rationalization of a fraction. All this really means is I don't want to have a radical, a square root, or some sort of root or a radical in the denominator. Okay? So, first thing we're going to do is we're going to take a look at this and see why this might even take place. If I had 1 over square root of 3, the big thing is they don't want a radical in the denominator, and here is why. Okay? So let's take an adventure back to what division is. Division and fractions are the same thing. Okay? You hated division when it was brought up with you back as a kid because it didn't work real well. And then we tricked you and brought fractions in, which is the exact same thing. So no wonder why you hate fractions as well, because it was just that. So let's say we had some random problem, which is 3 over 4, which really means 4 goes into 3 how many times? And if you remember division correctly, if it doesn't go in there evenly, you need to take it out however many decimals might have to take place. So if you were to do this, this becomes 4 doesn't go into 3. Bring the decimal straight up. 4 does go into 37 times. 7 times 4 is 28. I need to subtract these. I get 2. Bring down the next 0, and I get a 0. 4 goes into 25 times. They subtract. Nice thing is this is a terminating decimal. So you find out that the decimal equivalent to 3/4 is 0.75. Well, the reason why they wanted you not to have this in the denominator is because this. This means this. Root 3 goes into 10 how many times? Oh, I don't know. Doesn't make sense to me. Okay? That's basically why this portion of math is going to take place, because this is really hard math. And it's really hard math as it sits. If you were to try it, if you're really good at long division, it's still really long, hard, tedious math. So what they decided is the radical cannot be in the denominator. So what I'm going to do is, in order to bring the radical up, I'm going to multiply both the top and bottom by root 3 and root 3. Root 3 over root 3 is the same thing as 1. So if I take 1 and multiply it times a fraction, does the fraction change? So if I had 3/4, and I said 3/4 times 1 over 1 is still 3/4. Okay? So being that root 3 over root 3 is equivalent to 1, this fraction size does not change. It just makes it easier to do. Okay? So what do you guys think 1 times root 3 would be? Root 3? Cool. And then root 3 times root 3 is root 9. So root 3, I don't know what that is, but what is root 9? 3. So this is a simpler version, which now this means 3 into, and this is still ugly. This is still ugly, and I'm not going to ask you to do that, but that's where this is easier, where I'm taking a whole number and going into something versus a radical and going into something. So that's why this math is taking place. Now, With the invention of the scientific calculator that allows you to do larger stuff, this is kind of an outdated practice, but it still does indeed help you along further when you get into later math classes. And it doesn't have to just be calculus that you deal with this concept. You deal with it in statistics. Okay? Now, one thing I will tell you all about statistics, and please, you guys are all choosing your own path to what you want to be in life, and that makes you a beautiful person, and I can never take away from that. And I don't ever want to take away from that. But I would strongly urge you to take statistics courses. They're hard. They really are. But this is why I want you to take statistics. People will start talking like this and expect you to think it's the gospel truth. And you might have heard this type of conversation before. Watch any news station, and you're going to start hearing terminology like this. Well, we know that 20% of 1/5 of those people that went over to that country and dealt with that, only 19% came back. And those 19% came back, 1/5 of them had this type of opportunity available for them back in this country. And people are like, he's right. What the hell did he just say? He said nothing. He said gibberish. And people are like, he's right. Listen what he says. He had numbers in there with percents. And people thought, this has got to be true. No. Call bull poop on it. I'm telling you this because you as society and me as society and us as society get influenced by numbers. Yeah.
So go to such and I just disagree.
I was having a conversation with a student, and the conversation was dealing with the concept of a topic of marijuana. And so a lot of the argument with marijuana. Now, my whole gist on marijuana is, hey, if you ain't hurting me, and you're not destroying society, I can't stand in your way. Now, you're going to get people going, well, how many people are on marijuana beat their wives? Okay. Well, I will tell you this. I don't have either of those figures known to me. But somebody out there is going to hear some story going, oh, when was the last time somebody got in their car and was driving with marijuana and got in an accident? I don't know. I'm not privy to that information. I haven't gone and researched it. But that doesn't mean the validation of your point is any better. So this particular student tells me, well, I know like 4 little kids with cancer that because they use marijuana, they feel better. And I looked at this 16-year-old kid and said, you know 4 kids with cancer? And then the story started to change. Well, maybe not 4, but I've heard of some kids. That's where the argument went. Is it a viable argument? No. Okay? Somebody read on Facebook, somebody saw a tweet, somebody followed Instagram. Did I say all that right? I don't know. I'm not that. MySpace. Someone's on LinkedIn.
I actually have a MySpace.
So somebody saw something published and was like, oh my gosh, this is the gospel truth. It's on Facebook. We got to follow it. But the problem is the statistics that are used out there are used to influence you. And a lot of times it's fictitious. And I'll give you one last fictitious term. 80% of statistics you hear out there is made up. Did I just make something up? Yeah, I just said 80% of statistics. That's something you're like, oh, he's right. It's got to be right. Sounds about right. Do I know what part of statistics is made up? I have no idea. The what? Absolutely.
I could say 90% of the world is dead. And somebody'd be like, oh, okay.
I understand.
That sounds about right. Like if you put some
I understand, but that's why I want you to become literate with how statistics works, because it's used so often to try and influence you. Now, I will tell you, a good story always starts with some sort of statistical BS. And everyone loves a good story. But it's a story. So realize a lot of stuff out there that is being used to sway you. It's being used to sway the media. Now, the media, during a live interview, would sit there going, so what do you think about this? And hold a microphone in someone's face and we're like, well, 26% and 19% and 4% and 5%, and then 1/5 of those and 1/4 of 1% is. Oh, thank you very much. So back to you, Jim. And so we've no longer been able, now we're watching this as entertainment. We're like, oh my gosh, look at this moron they pulled off the street that actually spews data who knows something. No. It's like when a tornado hits. Hey, you guys, don't have lots of teeth. Come here. We want to interview you. Yeah, it's in my truck. I see this big thing coming out of the sky. So my first instinct was get my camera.
Put it on YouTube.
So, sir, you didn't want to get out of the way? No. Why not? You lost your wife and family, and your trailer is now in that tree. I know, but I got it on video.
So it's okay.
I'm gonna get a lot.
Go ahead.
Is this the lesson you wanted to teach us?
A little bit. You mad at me now?
We're done.
No.
I'm giving you real life. All right. Some geneticists say. There we go. All right. Learning. This is how easy this is going to be. Y'all ready for this? All right. Someone always gets mad when I bring up, the 1980s dance thing. You get all the white guys in the... Man, you dance good. Learned well. All right, I can't have a radical in the denominator. So I had just shown you, before I got onto the tangent about statistics, that I need to do this and this, both top and bottom. So 1 times root 2 is root 2. Root 2 times root 2 is root 4. Root 4 is what? 2. Done. Okay? I think you can talk me through this next one. I can't have a radical in the denominator. We're only going to multiply top and bottom by root 3 and root 3.
60% of people can probably do.
2 times root 3 is how much? No, not root 6. Unlike terms. What? No. Anyone? Yo.
2 root 3.
Yeah, buddy. 2 root 3. Root 3 times root 3 is how much?
1.
Say it as root 9. Root 9 is? 3. Okay, I can't have a radical in the denominator. What are I going to multiply top and bottom by? What? Root 7. Root 7, root 7. 1 times root 7 is how much? Root 7. Root 7 times root 7 is? Root 49. Root 49 is? 7. Okay. Can't have a radical in the denominator. What am I going to multiply top and bottom by? Root 2. 6 times root 2 is what, Kruger?
6 times root 2 is 6 to 2.
Root 2, good. Root 2 times root 2 is? Root 4. Root 4 is? 2. Oh, wait a minute. Curveball. We have a fraction that we can reduce. Outside and outside. 6 over 2 is?
3 over 1.
3 over 1. 3 times root 2 is 3 root 2. Done. Sometimes you can reduce the fraction. Oh, that's good. He's really good.
If we don't lose points or something.
Heck yeah. Shave your eyebrows off. All right. Almost done. Almost done. Can't have a radical in the bottom. What should I do?
Fix it.
Fix it. Okay. Root 5, both top and bottom. What is 15 times root 5? 15 root 5. What is root 5 times root 5? Root 25. What is root 25? 5. Curveball here. What do we got?
5.
5 goes into 15 how many times? Hey, notice I didn't reduce in the radical, did I? 3 root 5. Done. Almost done. Last one. Ready? Ready? Here we go. Can't have a radical in the denominator. Let's go. What should I do?
Root 7.
Multiply top and bottom by root 7, root 7. What is 42 times root 7? 42 root 7. Good. Root 7 times root 7 is root 49. Root 49 is? Wait a minute. Something here can happen. What can happen?
Divide by 7.
Yeah, 7 goes into that. How many times? 6. So I get 6 over 1, so I get 6 root 7. Done. Guys and girls. Worksheet number 22. And I just heard that the bookstore got more of these in, so it's $4 to go get one. Okay? I will tell you this right now. I want you to do problems 1 through 15. You want to know what's really cool? That's 1 through 6 right there. Yeah!
What about this picture?
What about, hold on to it, or throw it away? I'm putting the points in for you. It's on video. It's right there. It's right there. And that's on video too.